When arborists talk about tree work, this is the chapter where the craft really comes alive. Climbing, rigging, and removal combine biology, physics, and technical skill. Every movement in the tree, every rope choice, every knot, and every cut affects safety and efficiency. For arborists preparing for the BCMA exam, understanding these systems is essential. Not just the terminology, but how everything interacts under load. Because once a climber leaves the ground, the entire system depends on friction, anchors, rope construction, and controlled force. In this podcast, we'll explore how arborists access trees, how climbing systems work, and how rigging techniques safely manage large pieces of wood during pruning and removal. Let's start with the foundation of all climbing and rigging work: rope. Arborist rope is not just rope. It's engineered life support equipment. Traditional tree work used 3-strand rope, which is strong but stiff and less comfortable for modern climbing. Today, you'll more often see braided rope constructions like 12-strand rope, 16-strand rope, and 24-strand rope. These braided ropes improve handling and strength while reducing twist. Many arborist climbing lines use double braid construction, where a braided core and braided sheath share the load. Another construction is hollow braid, where the rope has a hollow center. Some ropes use Kernmantle rope design, where a load-bearing kern core is protected by a mantle sheath. You may also hear the term hard lay rope, which refers to rope that has a tighter twist and tends to hold its shape. All of these are types of rope, but arborists also talk about rope systems. A climbing line, a rigging line, or a load line may all look similar, but they are designed for different forces. The working load and the working load limit, often abbreviated WLL, are crucial safety concepts. The working load limit represents the maximum load that should be applied during normal operations. The rope's ultimate strength may be much higher, but safe systems stay within the WL. Another important concept is cycles to failure. Every time a rope is loaded and unloaded, it experiences stress. Over time, repeated loading cycles weaken the rope. Now imagine you are arriving on a job site to access a large oak tree. The first step is usually establishing an access line using a throw line. The throw line allows you to set your rope over a high branch that becomes your tie-in point. Once the rope is set, you're working with a climbing system. Arborists use 2 primary systems: a moving rope system, abbreviated MRS, and a stationary rope system, abbreviated SRS. In an MRS system, the rope moves with the climber, while in an SRS system, the stationary working line stays fixed, and the climber ascends using mechanical devices like an ascender. Climbers often use footlock or footlocking techniques, and sometimes a secured footlock to ascend efficiently. The climber is supported by a climbing saddle, also called a harness, specifically a work positioning harness with D-rings for attachment. A safety lanyard or work positioning lanyard provides additional stability when working near the trunk. In removals, climbers may also wear climbing spurs. Each spur has a gaff that penetrates the bark for secure footing. Of course, personal protective equipment matters too. A climbing helmet protects against falling debris, and a scabbard safely stores the chainsaw when not in use. Now here's where knots and hitches become critical. A knot forms a fixed structure in rope. A bend joins 2 ropes. A hitch attaches rope to an object. For example, a bowline creates a fixed loop that will not tighten under load. A running bowline creates a sliding loop often used to secure limbs. Other knots arborists use include the figure-8 knot, sheep bend, slippery bend, double fisherman's bend, and stopper knot. You'll also see looped knot structures like the alpine butterfly or a midline loop that allow attachment without accessing the rope ends. The parts of the rope matter too. The standing part carries the load. The running end or working end is the free end used for tying. Loops, bites, and wraps describe rope shapes. A loop crosses over itself. A bite is a U-shaped section without crossing. A wrap describes the rope going around an object. Hitches are especially important in climbing. Traditional systems use the Blake's hitch or tautline hitch as adjustable friction hitches. Modern climbers often prefer advanced friction hitch designs such as the Distel, Michoacan, Valdotain Tresse or VT, and Michoacan Tresse or MT. These are all types of friction hitch used with a split tail or Prusik loop. The hitch is connected to the rope with a carabiner. Many of these carabiners use double locking gates for safety. Others use single action gates with a locking snap mechanism. The gate is the opening part of the carabiner. Additional hardware may include screw link connectors, connecting link hardware, or snaps. To help manage slack, climbers may add a hitch tender or slack tender, often combined with a micro pulley. Sometimes climbers use friction devices like a figure-8 descender or the Munter hitch for controlled descent. Friction is the key principle here. Every hitch, pulley, or friction device manages the interaction between rope and hardware. You may also hear about friction-saving devices like a false crotch or other friction-saving device that protects the tree and rope at the tie-in point. These devices create a fair lead, meaning the rope runs smoothly without sharp angles that increase friction or damage fibers. Sharp angles are measured using bend radius and bend ratio. If the bend radius is too small, the rope experiences excessive stress. Now let's shift from climbing to rigging. Rigging is the art of lowering or moving wood safely during pruning or removal. A climber sets a rigging point in the tree and installs equipment like a pulley, arborist block, or snatch block. The arborist block is a heavy-duty pulley designed for large loads. Rigging lines run through the block and down to the ground crew, where the rope is controlled by a lowering device such as a bollard or porta wrap. The ground worker wraps the rope around the device to add friction. Each wrap increases control. The section being lowered is attached using techniques like butt tying, butt hitching, or tip tying, depending on how the piece should move. Sometimes arborists use natural branch union rigging, where the rope runs through a strong branch union rather than hardware. Another technique is blocking, where pieces are lowered vertically from a spar during removals. In complex rigging systems, arborists may build mechanical advantage systems, like a block and tackle or a Z-rig. Balancing loads is also possible using tools like an adjustable balancer, fixed-length balancer, spider balancer, or loopy. Rigging hardware may include rope sling, dead-eye sling, fixed-eye sling, eye-to-eye sling, spliced-eye sling, or webbing sling. Many of these use an eye-splice or eye-spliced rope to create permanent loops. Adjustable slings like a whoopee sling allow quick length changes. During lowering, forces can multiply dramatically. Arborists must consider anchor force and reaction force at the rigging point. Dynamic load occurs when a piece begins to fall before the rope catches it. This creates shock loading, which dramatically increases stress on the system. The longer the fall distance, the greater the dynamic load. Arborists refer to this simply as fall. This is why managing the rigging line and keeping it taut matters. Too much slack increases shock loading. Groundworkers also use taglines or pull line systems to guide wood safely away from obstacles. A speed line, sometimes called a zip line, allows pieces to slide along a sloped rope to a landing zone. Now let's talk about chainsaw cutting techniques during removals. Tree removal often begins with felling. The direction of fall is controlled with a notch, also called a face notch or face cut. Common styles include the conventional notch, open face notch, and Humboldt notch. The notch creates the hinge, which is the uncut wood between the face cut and the back cut. The hinge cut controls the fall direction. If done improperly, dangerous failures can occur. One of the most infamous is the Barber chair, where the trunk splits vertically. Specialized cutting techniques help prevent this. Arborists may use a bore cut, plunge cut, or snap cut. Other saw cuts include scarf cut, kerf cuts, and kerf management to prevent saw pinching. When felling large trees, arborists insert a felling wedge into the kerf to keep the cut open and influence the fall direction. Once the tree is down, the process continues with limbing and bucking. Limbing removes branches. Bucking cuts the trunk into manageable sections. Climbers performing removals from the tree sometimes use techniques like the fishing pole technique or drop start to control pieces. In some cases, the climber establishes a double tie-in or double tie-in system for extra security. Climbers may also establish anchors in different configurations. An anchor may be a floating anchor or a fixed anchor depending on system design. Sometimes the base of the tree is used as an anchor block for rigging systems. Now imagine you are inspecting a large removal job. You notice the rigging line passes through an arborist block at the rigging point. The ground crew controls it with a porta wrap attached to the trunk. The piece being removed is secured with a running bowline and stabilized with a half hitch and double half hitch. The rope passes cleanly with a fair lead. The system stays within the working load limit. Understanding these details allows you to evaluate whether the system is safe. This is also where exam questions often focus. The BCMA exam may ask you to distinguish between a knot, hitch, and bend, or identify when shock loading might occur. You might also be asked about the difference between a moving rope system and a stationary rope system, or how bend radius affects rope strength. As we wrap up, remember that climbing and rigging are systems built on interconnected components. Rope construction affects friction and strength. Knots, hitches, and hardware determine how loads are transferred. Rigging devices like pulleys, arborist blocks, and lowering devices control movement. Cutting techniques like face notch, hinge cut, and bore cut determine how wood behaves during removal. Every component must work together to manage load, friction, and force safely. In the next chapter, we'll shift from working in trees to diagnosing tree problems. Understanding how arborists investigate decline, identify causal agents, and separate symptoms from signs is one of the most important skills for a master arborist.
Thanks for listening to the Arborist podcast. Let's keep building your arborist knowledge one domain at a time. If you found this useful, please like and subscribe.